differential equation, dy dt is the sine of 2t times y. Is the equation linear? Yes. Is the equation homogeneous? Yes. Good. And then everybody gets to number 2 right. Okay, so thus far we have learned only one analytic technique for finding the solution to a differential equation. That's separation of variables, right? So we have just that one technique. It's very limited because it only applies to a very special kind of differential equation. We do have some qualitative and numeric techniques that we've studied. They can be applied to a much wider variety of equations, but they can't give you a formula, right? They can help you study the solutions as a picture or get numerical values for the function, but they can't give you a formula. So the problem of finding analytic solutions is actually a really tough problem because although the existence theorem guarantees that solutions to most nice differential equations exist, there's no guarantee that they're made up of the kinds of functions we're familiar with, like exponentials, polynomials, trig functions. In fact, usually they're not. Usually they're much crazier than that. There is no one general approach to solving a differential equation analytically. So over the 300 years that differential equations have been studied, mathematicians have developed many solution techniques that can be applied to just special classes of differential equations. In our course, we're going to cover a handful of those special techniques. And today we're going to develop one of the standard techniques for solving a linear differential equation. And this is handy because in Calc 1, you learn how to linearize things. So even when you have nonlinear differential equations, you typically can linearize, apply this technique, and at least get a good approximation of a solution on a small interval. All right, so a first order differential equation is linear if you can write it in the form dy dt equals some stuff with t's in it times y plus some other stuff with t's in it. So a of t and b of t just means a function of t's, so some stuff with t's. In other words, a differential equation is linear if it's linear and it's dependent variable. So you can identify its dependent variable from the dy dt, right? Y would be the dependent variable, t would be the independent variable. And if it's linear in the dependent variable y, right? If that y there just is a y to the first, we call it linear. All right, so let's look through this list and see which ones can we identify as linear. How about this first one? Yes, because that's t squared y to the first, right? So it's a function of t times y to the first plus another function of t. So this one's linear. How about this one? It is linear, yeah. We've got a function of t times y to the first plus another complicated function of t. The functions in t can be as complicated as we want. What we're looking for is the y to the first. So this is linear. Yep, we don't care about anything with t's. I'm looking at the y's. Okay, how about this third one? Yes, it might help if you solve for dy dt so that it looks like, so you have 3 plus t, 3 plus t times y plus 2. Yeah, so that's definitely linear. Function of t times y to the first. How about dy dt equals negative 2y plus 8? Yes. Yep, that's linear. We just have a y to the first. Okay. Dy dt equals y squared? No. Right? Y squared is not linear in y. How about dp dt equals e to the 2tp minus sine t? Yes, it's linear, and this is the first one that's a little bit tricky in that I changed the name of the dependent variable to p. So I'm looking for p to the first now. All right, dw dt equals sine of t times w. Linear, because the dependent variable is w. We are linear in the dependent variable. And dz dt equals t times sine of z. No. Right. The z is the dependent variable. Sine of z is a nonlinear term, so this is non-linear. Good. All right, linear differential equations come in two flavors. If b of t is 0, there is no plus some stuff with t's. So when you're looking at this formula, a of ty plus b of t, if that guy's gone, right, if there is no plus b of t, then we call the equation homogeneous. Also, we sometimes call it unforced. Yeah. Otherwise, it is non-homogeneous or forced. Okay. All right, so each of these, one is homogeneous, one is non-homogeneous. How about this first one? Homogeneous, yeah. So this is like my a of t, right? I have a function of t times y. There is no b of t, so this is homogeneous. And the next one, yes, this is your b of t. What's your a of t in this case? 1, yeah. So this is non-homogeneous. All right, every non-homogeneous linear equation that looks like a of t y plus b of t has an associated homogeneous linear equation where you just drop the b of t. You just get rid of it, and we call that the associated homogeneous equation. So from number 6, the one we just did, right, the one that was non-homogeneous was y plus sine of 2t. This is dy dt equals, right? I want to write down its associated homogeneous equation. So you just drop the b of t and you get dy dt equals y. Okay. Good. So now that we've covered the vocabulary, we can talk about this procedure for solving a linear differential equation. You can read the text for the reasons why this works. We're just going to practice it right now. So step 1 is find the general solution to the associated homogeneous equation. So just drop the b of t and solve using separation of variables. Step 2, you have to find one particular solution to the non-homogeneous equation. That is, you have to find some function that makes the non-homogeneous differential equation true. This step is often referred to in your book as lucky guess, right? Because you have to kind of guess at it. Right? Sometimes you have to guess more than once. And then to obtain the general solution of the non-homogeneous equation, add the results from step 1 and 2. Step 2 is the hard part in this process. We can sometimes find a particular solution by guessing smartly, but we do just have to guess. Will you guess smartly? We'll go over a couple so you'll see. Educated guesses, yeah. All right, so we're going to verify that the procedure works for a sample linear differential equation. For demonstration purposes, I'm going to give you the guess part on this one. I'm going to tell you a function that works, and then afterwards we'll talk about how you would have guessed it. Okay, so step 1 is to find the general solution to the associated homogeneous equation using separation of variables. So I just drop the b of t. So this becomes dy dt equals cosine of t times y. And once I've dropped the b of t, this becomes separable, and I can solve by separation of variables. So I'm going to have 1 over y dy equals cosine of t dt. Just get all the y's on one side, t's on the other, and take the integral of both sides. So antiderivative of 1 over y, ln y. It's technically the absolute value, but that's kind of a subtle point. I'm just going to ignore it for now. The integral of cosine is sine. Let's see, yep. All right, how do I solve this thing for y? Close, raise e to both sides, yep. I know. We raise e to both sides, so I get y equals e to the sine of t plus c, right?
And then you can separate it.
Yeah, and then we do this trick that comes up a lot where this could be rewritten as e to the sine of t times e to the c, because when you have like bases, you would add the exponents, but then e to the c is just another arbitrary constant, so I simplify and I get y of t is c e to the sine t. And often we put a little h here to represent that that's the solution to the homogeneous equation, right? It's not the solution to our original. All we did was solve the associated homogeneous equation. Right, it just means homogeneous. You don't have to write it if you don't want to. Just help keep track of what it is. What are you asking about, Kyle?
Oh, like in the book, they would only side, like they solve the left-hand side of the integral. Like they solve for e and then just put e to the right-hand side. I don't know. Oh, so it doesn't matter. Never do the integration. It would just.
Oh, they would do e to this integral. Oh, okay, yeah. Right. B of t, yeah. Yeah, when you do an actual example, it's much prettier. Okay, so this is the guessing part. This is the part where you have to guess a solution to the original full a of ty plus b of t equation. So I'm going to write down my equation, the whole thing, dy dt is cosine of t times y plus 1/5 times 1 minus t cosine t. So I have to guess a solution. I haven't told you how to do the guessing yet. So at this point, I'm going to tell you a solution, and we're going to confirm that it works, that it actually is a solution. All right, and this is good practice because there definitely will be a question on your first test where you have to just show that something is a solution to a differential equation. Okay, so I'm telling you that y of t equals t over 5 solves this differential equation. So that is a solution. So that means that if I plug this guy in to this equation, I get a true statement. So let's just verify that. So if y of t is t over 5, what is dy dt? 1/5. Good. So I'm just asking you to take the derivative of t over 5, right? You get 1/5. I'm going to write it over here because I might have to do a lot of algebra here. Okay, does that equal? Then on the right-hand side of the equation, I plug in wherever I see a y, I'm going to replace it with a t over 5. So I have cosine t. Instead of y, I have t over 5 plus 1/5 times 1 minus t cosine t. All right. If this equation is true, then I have confirmed that t over 5 is in fact a solution. All right. So this is t over 5 cosine t plus 1/5 minus, distributing my 1/5 here, t over 5 cosine t. Then I have two of the same terms. One's positive, one's negative. Right, so 1/5 equals 1/5, check. Okay, so t over 5 is in fact a solution to this differential equation. This really ugly looking differential equation. It's long, there's a lot of pieces to it, but we have a solution. And again, I'll tell you how to guess a solution later, but just knowing now that we have one, we can apply it to this procedure. So step 3 is to find the general solution. Oh, and I should tell you that also we often put a little, and again, it's optional, but your textbook does it. They'll often put a little p right there to mean y particular. one particular solution to the differential equation. All right, and then to find the general solution to the non-homogeneous differential equation, you have to add the general solution from part 1 to the particular solution from part 2, and that sum will be your general solution to the differential equation. There can be multiple particular solutions, yeah. Any differential equation has infinite solutions. You just have to find one of them in step 2. Yep. Yep. Okay, so y of t, which sometimes we put a little g to mean general. You don't have to, but the general solution is typically your homogeneous solution plus your particular solution, right? So in our case, the general solution is going to be c e to the sine t. That's the part we found in step 1. And then the part we found in step 2 was t over 5. Or we didn't find it, but we confirmed that that was a particular solution. This is a general solution to the differential equation. And we should verify, just like we did with the particular solution, that this works. So I'm going to write down my whole differential equation. So dy dt equals cosine t times y plus 1/5 times 1 minus t cosine t. And now I just plug things in. Anywhere I see a y or something related to y, plug it in based on the solution, y sub g, and verify that you get a true statement. So I'm looking for dy dt, right? That's the derivative of the solution. What is the derivative of c e to the sine t plus t over 5? Yep. C e to the sine t, right? Times the derivative of the stuff, the cosine t, the chain rule. Okay. Plus the derivative of t over 5 is 1/5. Okay, so that's dy dt, the derivative of the solution we found. And then on the right-hand side of the equation, you just replace the y with the solution we found, y. So this becomes cosine t times y, which is c e to the sine t plus t over 5 plus 1/5, 1 minus t cosine t. And we just verify that that is a true equation, that that statement is true. And we'll know that we have a solution. Okay, so on the right-hand side here, I'm going to distribute my cosine t. So I get c times cosine t times e to the sine t plus t over 5 cosine t. And then here I'm going to distribute my 1/5, and I get 1/5 minus t over 5 cosine t. I have some cancellations happen. I have two terms, t over 5 cosine t. One's positive, one's negative. So those cancel. And does the left side equal the right side? Yeah, they both have a 1/5 on them as a term, and they both have a c cosine t e to the sine t. All right, so we can confirm that the method works. The method actually does give us a general solution. Okay. And we can confirm graphically. I made a slope field using a computer. And then I graphed several equations that had the form c e to the sine t plus t over 5. I just chose some random c's, and I plotted these equations, and they fit perfectly over the slope field. And then the t over 5 was a special one. It was a straight line through the slope field. All right, so about the guessing step. It's time we do that. So here's another linear, non-homogeneous differential equation. dy dt equals negative 2y plus e to the t. The first step of the process is to solve the associated homogeneous equation. So first thing I want to do is solve dy dt equals negative 2y. Just drop the b of t term. You can solve this by separation of variables, and you get y sub h for the homogeneous is c e to the negative 2t. You can verify it by doing the work on separation of variables on your own. Step 2 is the guessing step. This is the step I want to focus on here. So it can be, typically, it makes it a little easier to guess if you put all of your y terms on one side. So if I rewrite my differential equation, dy dt plus 2y equals e to the t. And then you can kind of think through what kind of function could do this. What kind of function could you add its derivative to 2 times itself and get e to the t? So when you add a derivative plus 2 times itself, these two guys would have to be like terms, right? In order to get one term as the answer, you'd have to be able to add them together. So what kind of function and its derivative are like terms? E to the something, like e to the t, yeah. Yes, something times e to the t. So that's how we guess, and that's the part we don't know, right? So here we would have a guess that y particular is something times e to the t, alpha e to the t. We don't know what alpha is. So if we know that y particular is alpha e to the t, then when I do dy dt, what's the derivative of alpha e to the t? Alpha e to the t again. Okay, good. So we come back over here, and I'm going to plug in dy dt and y into the differential equation. So dy dt is alpha e to the t. 2 times y, replace y with alpha e to the t. That has to equal e to the t. And now I can try to figure out what alpha has to be to make this work. Well, you can combine like terms on the left here, right? What's alpha e to the t plus 2 alpha e to the t? 3 alpha e to the t has to equal 1 e to the t. And so your coefficients would have to be the same. I don't know. It could be.
I remember one that was
Probably. Yeah. So now my coefficients would have to be the same. There's a little hidden 1 there, right? So it turns out that 3 alpha and 1 must be equal to each other. 3 alpha would have to equal 1, which means alpha has to be 1/3. So that will work. My y particular, I guessed a form of what y particular would have to look like, and then I figured out what the coefficient has to be to make it work. So my y particular turns out to be 1/3 e to the t. And you can always check that it does satisfy the differential equation. Yes, if you guess wrong, you just will not be able to solve for alpha. Or you get something that doesn't make any sense. Yeah. Yeah, right. And then you'd go back and try a different format for y particular. And in fact, sometimes that happens. And a good trick of the trade is your second guess. Your second guess will often just throw a t onto it as another factor. Don't know why it works, but it does. Okay. So keep that in mind when you're doing the activities. If your first guess doesn't work, sometimes it works to just add a t to the another factor of t to your guess. So to find the general solution, we just have to add y h and y p, y homogeneous and y particular. So my general solution, my homogeneous solution, which was c e to the negative 2t, add on my y particular, 1/3 e to the t. So that process of that we used to guess the particular solution, where we guessed the format and solved for the coefficient, is called the method of undetermined coefficients. So this is a really, really good guideline for how to choose what the format of your guess. Okay, so we were able to choose alpha e to the t. There are lots of other formats for guesses. In general, your guess for the particular solution is made up of a combination of the same type of functions contained in b of t and the derivatives of the functions contained in b of t. So in our case, b of t was e to the t, so I only had to use alpha e to the t because its derivative is also e to the t. But if my b of t had been sine of t, right, my guess would have been alpha sine of t plus beta cosine t. You want to use the function that shows up and its derivative. Sometimes you might guess wrong. When this happens, just guess again, trying to learn from your first try. All right, try some.